Okay, good morning, everyone. I'm very sorry about that. I don't know what happened. Anyway, I think most of you met me at the induction event. So just to remind you, my name's Andrew Ross. So I'm one of the co-directors of the CDT, and I work in the School of Earth and Environment. My research interests are largely around kind of dynamical meteorology, so understanding weather processes in the atmosphere and how the atmosphere moves and behaves. I kind of started out as a mathematician, so my first degree was in maths. I enjoyed the applied maths aspects, particularly the fluid dynamics. I did a master's really focusing on that, and then my PhD was in kind of geophysical fluid dynamics, looking at gravity currents, both kind of modeling, theoretical work, but also doing laboratory experiments. So I've always kind of used a mix of approaches. And then after that, I saw a job opportunity in kind of meteorology, and I thought that was kind of vaguely related, and came to Leeds 20 years ago as a postdoc, and I've never got around to leaving. So my research interests now, as I say, are very much around understanding flow in the atmosphere, particularly the role of hills, mountains, and also interactions with the land surface. So today I was going to talk about a strand of work that's been going on for probably the last 10 years or so, looking at kind of cold air pools and fog in valleys. So you might not think of this as kind of extreme weather, but actually they can have quite a high impact. So on cold, clear nights, then we can end up with cold air pooling in valleys, and then that cold air draining down those valleys. And these cold air pools can lead to kind of really large temperature gradients and temperature differences within and outside valleys. And that can pose a significant danger for things like road icing, frost damage to crops, fog formation. It can prolong snow cover in these kind of cold valleys if those cold pools persist for multiple days. And it can also lead to increased pollution with the cold air trapping the pollutants in the valley. And that's a big problem, for example, in parts of the Alps where you've got very urbanized kind of alpine valleys. So this is a really kind of challenging forecast problem, particularly kind of on the UK scale, because this is very small scale processes. Okay, so here we're looking at kind of small valleys of the order of a kilometre or two across, maybe a couple of 100 meters deep. And these flow within these valleys at night time is driven by very small scale processes, and that makes it very hard to represent in weather forecast models where you've got a relatively coarse kind of grid resolution. This cooling is highly dependent on the surface energy balance, so the interaction with the surface. It's not just the flow in the atmosphere, so the radiation is important. Another real challenge in these kind of stable nighttime conditions is that the turbulence can be very intermittent. So you can end up with periods of almost kind of laminar flow, and then you'll get a burst of turbulent activity, and those intermittent turbulence can be quite important in terms of things like mixing and transport. But most of our models of turbulence, our kind of conceptual understanding, is based on the kind of steady state idea of kind of fully turbulent flows, and that makes it really challenging to model these kind of intermittent turbulent conditions. And then particularly when we start thinking about the role of fog, the fog is really important, because if the fog forms, that completely changes the cooling and the radiative interaction with the surface. And that fog formation itself is really sensitive to things like how much moisture is in the atmosphere, aerosol particles on which the fog droplets form, and the actual kind of detailed microphysics of how those droplets form. So again, very small scale processes that are hard to capture in models. So this is a pretty challenging forecasting problem, and a lot of interesting physics going on here, interactions between the fluid flow itself and various other processes. So the Colpex project I'm going to talk about largely today is the aim was to really predict the near surface conditions in stable boundary layers better over kind of complex terrain for these practical applications such as frost and fog prediction. So really improving the kind of the high resolution understanding of those processes and ability to forecast them, and also to represent the effects of those small scale processes in larger scales in numerical weather prediction and climate models. So one of the challenges of kind of climate modeling is that in order to run these models over the whole globe for long periods of time, then you need to run at relatively coarse resolutions. And so there's lots of important processes that are not actually resolved in the flow, and therefore you need to parameterize their effects in the models. And there's a lot of research going on into what's the best way of parameterizing these different effects, and how can we do that accurately. So the project started off with a big field experiment, which ran over the winter, well, the kind of year 2009, 2010, so about 10 years ago now, with really focused observations from about September 2009 through to April 2010. And the field site was in Shropshire, so on the England-Wales border in the Clun Valley. So it's a beautiful part of the world. So a few photos there, and you can see it's kind of very gentle, kind of rolling hills. So many of the previous studies of cold air pooling have been on kind of much larger scale mountains, mountain ranges in the Alps or in the Rockies in the US, for example. But really, we were interested in kind of smaller scale UK kind of topography. So as I said, it was a collaboration between the Met Office, the University of Leeds, and the National Centre for Atmospheric Science. So we took a lot of enhanced observations over that autumn, winter, early spring, including a number of kind of IOPs, so kind of intensive observation periods, where we made really detailed overnight observations with additional measurements, things like launching weather balloons, and we had an instrumented car that we drove around as well. So there's an overview of the field campaign in a paper led by Jeremy Price in the Bulletin of the American Meteorological Society. So just to give you an idea of the kind of the field area we were looking at, this is the Clun Valley. So the green here is the lower part of the valley, you can see. And we had a number of transects here of kind of weather stations, and at the bottom in the valley, the squares or the diamonds here marked kind of the squares marked instrumented towers, where we were taking measurements at multiple heights up to kind of 30 or 50 meters above the ground and measuring turbulent fluxes as well as just the kind of mean conditions. And we also had some measurements in this smaller, more bowl-like valley here in Burfield, just in the bottom right of the map. And you can see, as I said, this topography, the squares here are kilometer squares. So the valley is maybe a couple of kilometers across at most, from kind of top to crest to crest. And up to maybe 200 meters kind of deep in places. So very kind of moderate rolling kind of topography, typical of much of lowland kind of UK. Despite the relatively modest kind of topography, we actually see some really strong cold pools. So this is just a snapshot of the temperature difference between two pairs of sites, so one on the valley floor and one on the summit, during March 2010, and you can see during the daytime, typically the hilltop sites are about a degree colder than the valley bottom sites, and that's just because of the environmental lapse rates and the fact that temperature decreases with height in the atmosphere. But you can see overnight we get these really big spikes. So not every night, but certainly on a large fraction of the nights, we see these big spikes when the temperature within the valley can be up to 5 or more degrees colder than the site, the hilltop site, which is maybe only 100 meters higher up. So you get these really strong inversions, big temperature differences occurring over relatively small differences in height. So this is just another way of looking at some of the same data. So this is now over the whole of the experimental period, so September through to April. And you can see that we get a real distribution of these cold pool strengths. So cold pools up to 5, 6, 7, or 8 degrees are relatively common, and these really high differences up to a kind of over 10 degrees we saw kind of a bit rarer. But you can see that there's a very high frequency of occurrence of these cold air poolings events. And if you look at that kind of by month, you can see that although you might expect these events to be stronger in winter, actually they occur all the way throughout the year. So if you get a nice clear night in summer, you'll still see the same kind of cooling going on in the valleys. The overall temperatures will be warmer, but the temperature difference between the valley and the hilltop will still be significant, even in kind of summertime. So alongside all the observational work, we also did a lot of modelling work with the Met Office Unified Model. So this is the model that's used operationally for weather and climate modelling, but it's also run at much higher resolutions as a kind of research model to really understand atmospheric processes. So in this case, we had a kind of it's a nested suite. So we used at that time what was the operational model was a 4-kilometre model, the UK4, and nested within that there was a 1.5 kilometre horizontal resolution domain which covered most of southern England, and then nested within that there was this very high resolution 100-metre model which was centred over the Clun Valley that we were interested in. So the operational UK4 model is initialized every 3 hours, okay, with kind of the global analysis. So, and that provided the boundary conditions for the other two models. So, so that's kind of constraining the boundaries to be near the truth. But the models internally were then free running. So we did some case studies, and we also did a kind of 2-month long run, essentially where the model was just being driven through the boundaries, and it was allowed to evolve internally as it would. And that allows things like soil moisture and internal processes to kind of spin up, for example. And we had 140 levels in the vertical, so with about 12 of the kind of temperature levels below 100 meters. So it's relatively well resolved for atmospheric models, and certainly higher resolution than we would be running operationally. So obviously, with any kind of modeling work, it's good to do some validation first to see how well the model compares with observations, and we did a whole lot of that. This is just one example. So the black crosses here show observations from one of the main sites in the valley at Dufferin. The green line shows the temperatures from the 1.5 kilometer model, and the red line shows the temperatures in the 100 meter model. So if we focus on the overnight period, so there's the minimum temperatures here, you can see that at 1.5 kilometers, the model tends to significantly over predicts the nighttime temperatures, essentially because 1.5 kilometers is not sufficient to really resolve these valleys, and therefore we can't really represent the cold pooling events at all accurately in the model. Whereas 100 meters does a reasonable job, and actually we get pretty close to the minimum, both in terms of the magnitude and the timing of that cooling overnight. Some nights are not quite so good, but overall it's a pretty good performance. So there's a clear benefit of the kind of 100 meter resolution over the 1.5 kilometers. It's worth noticing there is some daytime biases. Both the models are a little bit too cold, and that's due to other processes. So I won't focus on that here, but certainly that's something the Met Office were interested in and have worked to kind of correct in later versions of the model. So just to give you an idea of what the temperature structure looks like, we've got some contour plots, color contour plots here. So the color here is showing the temperature in the valley, so at 8 o'clock and then at 9 o'clock. And the arrows we can just about see show the flow. So you can see that 8 o'clock, which is a couple of hours after sunrise, you can see that cold air is starting to form within the valley here. You can see the valley's really nicely picked out in these greeny yellow colder colors, and then that cold air is coldest down at the bottom of the valley, and you can see that over the next hour the cold air is kind of moving up the valley, or the air is cooling within the valley, and you're getting an increasingly big temperature contrast between the valley and the kind of hilltops around it, which cool much more slowly. And if you look carefully, you can see that certainly by 9 o'clock, you can see we've got a kind of northerly airflow here. So over the hilltops, these wind vectors are kind of pointing to the south. So we've got northerly airflow, but within the valley, the flow is really decoupled, and actually the flow is down the valley, weak down valley flow, which is very different to the kind of the larger scale northerly airflow that we've got over the summits. So clearly the flow within and above the valley has become decoupled. And you can see that a bit more clearly in these kind of cross sections here. So we start off kind of average between 5 and 6 o'clock. So this is before sunset. You can see that during the day that the wind, so this is a north-south transect. So this is the north. You can see the wind blowing down into the valley and then back up the other side. And then as the sun sets and cooling starts, you can see we start to build up this temperature stratification here. So getting colder air in the bottom of the valley. You can see the air is descending part way down. When it reaches this kind of shallow cold pool, it then kind of separates and then lifts up over the top, and you've got kind of recirculating air in the bottom of the valley here. And as the night goes on, the cooling increases. We get a deeper cold pool forming until, as I say, by 9 o'clock, the air is essentially within the valley is completely decoupled, and we've got this very weak circulation down valley flow, and the air aloft is then just moving across the top of the valley. So we were really interested in this kind of cooling processes and what's driving these cooling processes. So we often think, because we've got this down valley flow, we kind of imagine that there's cold air being transported down the valley by these drainage flows, and that's leading to the cooling. And that was one of the things we kind of wanted to test. So there was some previous idealized modeling work by some of our collaborators at the Met Office that had suggested that actually this kind of sheltering mechanism is a primary cause of cold pool formation. So This decoupling of the flow within and above the valley means that the reduced winds in the valley reduce the turbulence and the mixing, and therefore the surface cools, but we can't transport warmer air down from aloft to counteract that, and therefore you end up with colder temperatures within the valley as a result of that in situ cooling, compared to outside the valley where the stronger winds can lead to more mixing and warming. So this idealized study was for kind of very simple 2D valleys, and then the questions was, well, what happens in real 3D valleys? So what is the role of advection transport, this sheltering mechanism, and the radiative cooling? So one of the nice things we can do in the model is we can really look in detail at the kind of the temperature, the heat budget equation. So look at all the terms that are changing the temperature in the model through the different processes, and see how those vary through the night and what's driving the cooling. So here we've got those different terms. So the hilltop site on the left and one of the valley sites on the right. So the black line shows the advection, so that's kind of transport. So you can see that at both sites that's a warming effect actually. So the winds, the flow is bringing warmer air towards the surface or towards these sites. These black and red lines have actually been divided by 4, so they all fit onto the scale. So that warming due to advection, cooling due to boundary layer processes, so that's really the turbulence and mixing. And you can see those two are by far the largest terms, but actually they kind of nearly cancel out. And then actually the cooling here, so the total cooling is that, so the sum of that advection and the boundary layer, the turbulent mixing, is that blue line there. So you can see that actually it has a slight warming, but it's really quite weak. Those two terms pretty much cancel. And actually at the hilltop site, what's causing the cooling is the long wave term. So this is the radiative cooling, the radiation that's leading to most of the cooling. Within the valley, we see a slightly different picture. So again, these advection and the boundary layer terms are large and largely cancel out. The radiative cooling does play a role, but actually it's the imbalance between the advection and the boundary layer term that leads to most of the cooling. So there's different processes going on within the valley and at the hilltop. But perhaps the surprising thing is the advection. So the transport down the valley, the drainage flow is actually warming the flow locally, and it's the mixing that's leading to the cooling. Okay, so this is some cross sections similar to what we looked at before, but now just looking at these individual components. So the top two here are looking at the advection at different points in the valley, and so you can see that right down near the surface, that advection is warming. Okay, so it's actually the air that's been coming down the valley is a bit warmer than the surface, but through most of the cold pool, it's actually having a cooling effect. So whether advection is warming or cooling, it depends a bit where you're looking in the flow. And then this boundary layer term right near the surface is cooling. Okay, so it's transporting that cold air from the surface into the flow, but actually further up in the flow, it may be having a warming effect. So again, mixing down warmer air, it could actually be warming the flow. So this picture we saw here from kind of the surface temperature does vary with height. It depends where in the flow you're looking as well. So it's quite a complicated kind of process going on. So from all this kind of budget work, we came up with a kind of schematic then of what we think is happening. So essentially, as I said, you've got this decoupled flow aloft. So the cold air in the valley prevents air aloft kind of making it down into the valley. We get the formation of a cold pool. So in the early evening, we see kind of cold advection from the valley side. So the air cools on the sides. That cold air flows down into the valley and helps the formation of the cold pool. And then later on in the night, we get this kind of down valley drainage flow setting up. So aloft, that might be cooling, and near the surface, actually, it can lead to some warming. But it's that drainage flow that maintains the non-zero kind of heat flux gradient. So there's this kind of cooling is enhanced by this drainage flow. It's enhancing that kind of turbulent cooling within the valley compared to what we would see outside the valley on the hilltop sites. So one of the really nice tools, just as kind of slight aside, that we can use to look at this flow is and to see these different flow regimes is to look at back trajectories. So essentially, if we take a flow field and we look at a parcel of air and we say, well, where did that air come from? Where did it originate? So we basically trace the flow backwards to find out what the trajectory of that air parcel was. So the top here, we've got some trajectories taken at kind of 4:30 in the afternoon, so well before sunset. And you can see, as you might expect at this time, if we start with these parcels of air in the valley and trace them, those parcels have come from the north, they've come over the hilltops and down the valley side into the valley. Okay, so this is this coupled flow that we see during the day with air flowing down into the valley, down the valley sides into the valley. But by later on in the night, so kind of 9:30, we look at the parcels from the same location here in the valley floor, and we trace them back. You can see that those parcels of air actually entered the valley right up at the top here. So they're flowing into the valley right up at the head of the valley and then all the way down the valley. So there's very little interaction between the flow in the valley and the flow aloft. So that's a really nice visualization of these two different kind of flow regimes that we can see. So that was some kind of general modeling work looking at understanding the temperature budget. So I wanted to talk a little bit about one particular case study that we looked at. So this was one of our intensive observation periods of the night of the 4th and 5th of March. And in many ways, this looked like an ideal night for kind of cold air pools to form. So we had high pressure situated over the UK, so very light winds. There was pretty clear skies. So this is an infrared satellite image from overnight, and you can see that over most of the southern part of the UK, there's very little evidence of any cloud at all. So clear skies allow that cooling to happen, and lack of winds allows the decoupling to happen, and therefore it's ideal conditions for a kind of cold air pool to form. And if you look at the temperature, so this is temperature from several of our different weather stations overnight. So the black one here was a kind of hilltop one. So you can see it cooled a bit, but then the temperature kind of stabilized and only decreased slowly overnight. Whereas these weather stations situated in the valley all cooled much more significantly, with a minimum temperature just around sunrise that was kind of significantly lower than the kind of the hilltop site. So the big picture is, yes, we had clear evidence of a cold pool forming in the valley at multiple sites. It cooled all the way through the night and until sunrise, and then rapidly warmed up as the sun started heating up the air, and the air became recoupled with the atmosphere above. But if you zoom in, you can see there's actually a lot more detail. So you can see these kind of warming spikes and here going on within the valley. And at one of these AWSs, then it suddenly kind of cooled even more substantially just near sunrise as well. So there's lots of smaller scale details going on here. That's quite interesting, suggesting it's not just a uniform cooling throughout the night at these sites. And you can see that some of these kind of warming events happen at multiple stations. So it's clearly something that's kind of larger scale. It's not just an isolated site or weather station. So we can kind of look at a bit more detail out there here. So this plot shows LiDAR measurements. So this is basically a upward pointing laser, and then that laser light is scattered off cloud particles or aerosol in the atmosphere, and the instrument detects those return signals, and by looking at the Doppler shift in those, it can measure how fast those reflecting particles are moving away or towards the LiDAR. So you can use that to measure kind of vertical velocity in the flow. So you can see here that throughout most of the night, the vertical velocity was quite low, and then about 11 o'clock, which was kind of what the first of those kind of warming episodes, you can see there is these kind of red streaks here. So we've got evidence of kind of stronger updrafts and downdrafts. So there's more vertical motion around the level of the hilltop. So kind of the top of the valley, the top of the cold pool, during this kind of hour, 2 hour period here. And then things settle down again. And then we had another episode about 1 to 2 o'clock in the morning. And again, you can see some increased vertical velocities, but this time, rather than being around hilltop, there's something further up that seems to kind of propagate down towards the valley, increasing the vertical velocity, and it's a more coherent structure. And then again, things kind of quieten down. And then we get this period before and after sunrise, where we start seeing increasing vertical velocity again, a bit more speckled, but more evidence of again of some mixing down, particularly around kind of sunrise. So there's clearly different things going on, and these kind of mixing events here seem to correspond with that warming that we saw in the surface temperatures. So they're mixing slightly warmer air from above the cold pool down into the cold pool and disrupting that kind of cooling. So the question is, what's causing these kind of intermittent events then? So there's actually a range of different things going on, and it just kind of demonstrates the complexity of trying to forecast these kind of events. So the first episode here, this is the zoom in of the LiDAR image. You can see these kind of vertical motions, so these kind of upward and downward motions that kind of look slightly wave-like. And actually, if we look at the radio on, so this is the weather balloon that was launched at 11 o'clock, so just in the middle of this period. One of the things we can look at from that is the ascent rate, so how fast it's rising, and this is a kind of proxy for the vertical velocity. Okay, so if the balloon's got a fixed kind of buoyancy, then changes in the ascent rate must be because the background flow is either assisting or kind of impeding that ascent. And what you can see is this kind of wave-like structure here in that ascent rate, suggesting that we're moving through patches of kind of increased and decreased vertical velocity. So we've got evidence of kind of waves in the kind of horizontal here near the hilltop. And then we've got evidence of this vertical wave structure here going up to kind of 6 kilometers in the atmosphere, so well up into the atmosphere. So what we think is happening in this case is there's some kind of larger scale wave activity, which is then impacting locally on what's happening near the valley top. And these kind of waves can be generated by things like flow over hills, and you get these internal waves that propagate through the atmosphere. So it may have been generated locally around the kind of Clun Valley or propagated from further aloft, and it's hard to tell with the observations we have. But it appears that this kind of wave activity is impacting on the kind of the local near valley flow and therefore on the actual cooling within the cold pool itself. Episode 2 then. This looks less like kind of wave activity. You know, as I said, we don't have that kind of changes in vertical velocity. Instead, we've got this patch of kind of vertical velocity that seems to be moving down, higher vertical velocities moving down towards the surface. So this looks more like something mixing down from aloft down towards the top of the cold pool. And if we look during this period here, we can see that this corresponds to an increase in the wind speeds near the hilltop. So the red line here is the hilltop wind speed, and you can see these grey bars mark the 3 episodes. You can see that during episode 2, we see an increase in the wind speed at the hilltop. Winds are still low in the valley because the flow is decoupled, but this increase in wind speed seems to correspond with kind of mixing of higher wind speeds, higher momentum air down towards the surface, and we see a signature of that in the LiDAR. And obviously that increased mixing then mixes not only momentum but some heat down into the cold pool and results in a kind of cessation of the or reduction in the cooling rate. And then the final episode later in the night, it is kind of similar in a sense that we see evidence of kind of mixing, but in this case we think it's specifically due to the formation of a low-level jet. So if we look at kind of the wind speed profiles here from radiosondes, so the black one was launched at kind of 4 in the afternoon before sunset. We've got one just after midnight and then one at 5:30 in the morning. And you can see the midnight one, the wind's kind of increasing pretty much with height as one might expect in the atmosphere. But by 5:30 in the morning, we've actually got a kind of maximum. We've got a peak in the wind speed about kind of 800,000 meters above the ground, and formation of this kind of jet structure. And this is something that we commonly see overnight in kind of these kind of cold conditions. So essentially during the day, we have a wind profile which is kind of balanced. So it's got a balance between the Coriolis force due to the Earth's rotation and the large-scale pressure gradient and the kind of turbulence. Nighttime, when the turbulence dies down, conditions become stable, the flow becomes imbalanced and accelerates, and then you get the formation of these jets. And the time scale of these jets means that they tend to peak later on in the night. Okay. And we see evidence of that again in the kind of the veerings, and the change in the wind direction is also characteristic of these jets. Okay. So it looks like we have the formation of this jet, and where we've got this jet, we've got obviously stronger kind of wind shear here, and then that instability generated by that wind shear can lead to additional mixing again around this kind of hilltop region, mixing warmer air down into the cold pool. So this was kind of a really interesting case study, and really demonstrated that even on what looks like a very ideal night for cold pool formation, there's lots of other things, small scale processes going on that can then modify how that cooling happens, and to actually capture all of that in a model is quite a challenge. So I said one of the other things that we wanted to be able to do is to try and think about what's the larger scale impact of this cooling, and can we predict that cooling based on relatively simple large scale measures of the flow, and that could be useful, for example, for downscaling. So if we can't afford to run a model over the whole UK at 100-meter resolution, can we use some of the information from the coarser resolution model to make predictions about when we would expect cooling to happen in particular kind of small scale valleys that we could use for then forecasting road temperatures, so local authorities know when to go out and grit the roads, for example. So here we're looking at the kind of the temperature difference in the valley, so the strength of the cold pool as a function of this parameter, this non-dimensional parameter here, NH over U. So N is a measure of the background stability, H is the depth of the valley, and U is the kind of the background wind speed above the valley. So these are kind of large scale parameters that we could get from a coarser resolution model. And then the color here shows the balance between the downwelling and the upwelling radiation. And you can see that actually there's really quite a good kind of collapse in this data here. So particularly for a given kind of radiation balance, so particularly kind of cloud conditions, you can see there's quite a strong relationship between this parameter NH over U and the temperature difference. So this suggests that these relatively simple scalings could be quite useful as a kind of tool for downscaling from kind of coarser resolution models to actually make predictions about the cooling in valleys. So as well as so I talked a little bit about some of the work we did kind of validating the high resolution model for one particular case study. We also did some work with the kind of the 2-month-long simulations, looking at the performance over a whole range of different conditions. So they're kind of providing a better overall assessment of how well the model does. When we plotted this up to start with, so this is kind of model temperature here, and then observations at this site in the valley at Dufferin. You can see that there's a clear bias in the model results of the model being too cold compared to the observations on a substantial number of nights. Some nights it's really good, but then there's quite a lot of nights where the model is just too cold compared to the observations. And clearly that's not at all ideal, so we kind of wanted to understand what's going on. So we started looking at observations we had to measure, and in particular looking at the radiation. So here we've got some plots of the long wave, the downwelling long wave radiation. So this is strongly dependent on the cloud cover in the model. And again, we've got on the y-axis the model downwelling long wave, and then on the x-axis we've got the observed long wave. And if you look during the day, so here mid-afternoon, you can see, and then the color shows you the temperature bias in the model as well. So if you look here during the day, you can see there's a fair bit of scatter, and some days it's warmer and some days it's colder, but there's no evidence of a clear model bias during the day. Okay, there are variations on the day-to-day, but there's no clear bias. Whereas if you look overnight, we can see that actually the simulated downwelling long wave is consistently lower overnight than the observations, and therefore the vast majority of the days there is also a cold temperature bias in the model. If there's too clear skies, then you end up with too much cooling and then too low a temperature. So there's clear evidence of kind of bias there in the 100-meter model. But interestingly, if you look at the 1.5 kilometer model, then you don't see that bias at all. Okay, so the points are now much more evenly spaced above and below the 1-to-1 line, and there's no clear evidence of a warm or cold bias. So there's something, even though with this 100-meter model, this higher resolution model is resolving the topography much better, clearly there's something wrong in the model, which means it's kind of introducing this kind of bias overnight in terms of cloud cover, and that's impacting on the predictions of temperature. And it turned out that actually this is all to do with these parameterizations again. So as I said, one of the challenges in numerical weather prediction climate modeling is that the range of scales in the atmosphere is so huge that we can't afford to run at high enough resolutions to resolve all the important processes, and we have to parameterize many of those. And one of the things we need to parameterize is what's happening in the kind of cloud formation processes. So if you imagine, so typically if we think about clouds forming, we expect clouds to form when the air becomes saturated, so the relative humidity reaches 100%. Okay, the air can't hold any more water vapor, and that water vapor has to start condensing out as liquid water to form cloud droplets. So imagine we've kind of got a grid box here. Okay. Now, if we only form cloud, and what's the relative humidity going to look like within that grid box? Well, there's going to be some subgrid variability in that box. So the relative humidity profile might actually look something like this within that grid box. Okay. So if we just look at the average, which is what our model's representing, the average value in that grid box would be here. So that would be well below 100% relative humidity. So if we just looked at the mean relative humidity in the grid box, we wouldn't predict there would be any cloud forming. But because of this variability, there might be individual points where actually the air does become saturated, and we do get kind of patches of cloud within that grid box, even if the whole grid box is not cloud covered. And therefore, one of the things that we do in the model is, rather than setting the relative humidity at which we expect cloud to start forming to be 100%, we actually have this RH crit parameter, so this critical relative humidity value, which is slightly below 100%. And that's essentially to account for this subgrid variability. Okay. And that parameter was kind of tuned for the 1.5 kilometer model, and it works quite well there. So we don't see any biases in the cloud cover in the 1.5 kilometer model. Now, what you might expect is, as you move to smaller or to higher resolution, you're capturing more of this variability anyway, and therefore that RH crit value should become higher as you go to higher resolution, because you've already captured more of the subgrid variability. So that's what we did in the initial model setup. But when we did that, we saw that we didn't get enough cloud, and therefore we ended up with too much cooling. So this is the kind of the cold pools that formed originally in the 100-meter model, and you can see we had far too many cold pools compared to the observations. So we reran a short period of this with a 100-meter model, but changing that RH crit value, so actually using the value that's used in the 1.5 kilometer model, so not accounting for the change in that parameterization with resolution. And when we did that, actually we saw something that looks much more like the observations. So we better captured the cloud cover, and therefore better captured the cooling in the valley. So I guess there's kind of two messages. This one is that although these cold pools are really governed by small scale processes, getting things like cloud cover wrong in the large scale can have a massive impact on the kind of the cooling, and therefore lead to kind of significant biases in the model. So you've got to get the large scale stuff right as well as understanding the small scale variability in processes. And the other point is that we still don't fully understand how this subgrid variability works, and that obviously our idea that this RH crit should increase with increased resolution is perhaps not completely accurate, and we really still need more detailed observations of the subgrid variability of relative humidity over a range of conditions, so that we can try and really pin down this parameterization better. And that's something the Met Office has been working on, as a result of some of these kind of the demonstrations from this set of experiments and from other experiments as well that they've been doing. So the final thing I wanted to say a little bit about then was this question of upscaling. So including the impacts of these kind of very detailed processes in kind of larger scale models. So as a result of this kind of cold pool processes, of a complex kind of topography, we would expect that there might be enhanced mixing going on compared to over a flat surface because of this enhanced shear induced by these kind of topographic flows. And so the MESOS currently has a parameterization for this, okay, which looks at the topography, tries to predict the cooling, and has an enhancement factor for the transport over kind of more complex terrain. And one of the things we wanted to do with these simulations was to try and actually test that idea. So you can run a high resolution simulation, use that as your kind of truth. Then you can do some kind of averaging to find out, what the mean flow looks like. Apply the parameterization and test that, enhanced mixing predicted by the parameterization against what you actually resolve in the high resolution flow. So we can use these high resolution simulations as a kind of an experiment to test and to develop our parameterizations. So we looked at the various things that go into this, so particularly the shear but also the buoyancy gradients, and this Richardson number, which is a diagnostic, which gives us a measure of the mixing we would expect. And it turned out these simulations suggest that actually the kind of current simple parameterization may not be a particularly adequate representation of the enhanced mixing due to these cold pools and drainage flows. Actually, that we might need a kind of more sophisticated approach in future. So to conclude then, hopefully you've kind of seen that the kind of dynamics of these cold pools can be quite complicated. There are lots of processes going on. It depends on the surface cooling, it's on the turbulence. There's a lot of things that we have to get right. It may surprise you just how ubiquitous these cold pools are, and they can be really significant even in very kind of moderate terrain where you wouldn't expect kind of those large temperature differences. That they can be really significant. High resolution simulations can kind of simulate what we observe broadly, and they give us a really useful tool to try and understand the processes that are going on. We can do lots of things in the model. We can look at all the different terms. We can balance energy budgets, temperature budgets to try and understand what's driving the flow and understand the role of different processes in developing these flows. I didn't really say much about the foggy cases, but they remain a real challenge, and there's a lot of work understanding the role of kind of aerosol and the microphysical processes there to get those foggy cases right. And as I say, there's still more work going on to actually translate some of this process understanding that we've got from these studies to look at how we can use that more practically in terms of downscaling temperatures for kind of forecasting or for representing the effect of these kind of small scale processes in global weather and climate models. Okay, so I'll leave it there. I'm happy to answer any questions if anybody's got, or if you want to email me afterwards if you think of anything. That would be great.